All right, so we are still in 4-4. We are working with the zeros still, except 4-4.
Good morning again. All right, homeroom teachers, please submit your attendance at this time. Any student now arriving late to your class, please make sure you send them for a late pass. Thank you.
Except 4-4 is now asking you for the complex zeros. It's no longer just asking you for the real zeros. So just remember, like I tried to explain yesterday, complex doesn't necessarily mean it has to be an imaginary number. A complex number can be real or imaginary. So basically, you are now responsible to find all possible zeros, whether they are real or imaginary ones, okay? They tried to give you some theorems to kind of guide you, because once the zeros start to become complex, some of our tricks like the rational zero theorem, synthetic division, they don't work anymore. So then it becomes harder and harder to find those zeros by hand, and the graphing calculator is not capable of telling you what a complex zero is because they don't appear on the graph and there's nothing for them to calculate. All right? So just to remind you guys from yesterday, the zeros to a polynomial function are complex numbers. That means they're either going to be real or imaginary numbers. According to the conjugate pairs theorem, imaginary zeros come in pairs. So if you have an imaginary zero in the form a plus bi, then you automatically know a minus bi is also a zero. They have to come in pairs. You took the square root of something negative. That's how you got an imaginary or complex number. And when you take the square root of square, it creates that plus or minus version, okay? All right. Another theorem. It says every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of, did you not get notes? I'm sorry, I handed them out. No. Sorry. Okay. Can be uniquely factored over the real numbers into a product of linear factors and or reducible quadratic factors. So yesterday there was a theorem that said every zero can be written as a linear factor. As weird as it looks, if 2i is a zero, then x minus 2i can be its factor, right? That's not normally a factor that we would have come across, but it could be used to create a polynomial function with that zero. All right, so now this theorem is saying it can be written as linear factors and or in irreducible quadratic. Your imaginary zeros will always form, their product will always form an irreducible quadratic. So let me show you. It's saying all of your real number zeros can become a linear factor. So if 2 was a zero, it could be x minus 2, a linear factor. All of your imaginary zeros come in pairs, and their product will always become an irreducible quadratic factor. So guys, let's say we had a degree 4 polynomial. So he has 4 possible zeros, right? Let's say -3, +5, 2i, and then -2i. Let's try and keep it pretty simple. So your real number zeros, they can become linear factors. X plus 3, x minus 5 would have been factors that created those zeros, right? Now they're going to multiply out to a quadratic as well, but their quadratic will factor to x plus 3 and x minus 5 or whatever they were, all right? But now your imaginary zeros, when you write them as factors, we could say this is x minus 2i, and we could say this is x plus 2i to have gotten those as zeros. Guys, have you ever worked with a quadratic and factored it into those two factors? No, right? They usually don't factor to these imaginary factors. So what they're saying is, really, your imaginary factors, your pairs, if you FOIL them out, if you multiply them, their product becomes an irreducible quadratic. And it's that quadratic factor that you most likely had set equal to 0 and solved and got those as your zeros. So watch if we multiply this out. X times x is x squared. X times 2i, as weird as that is, that's 2i x. -2i times x is -2ix. And what's going to happen to them? They're going to cancel out. And then -2i times +2i is -4i squared. So if we reduce this, they cancel. I'm left with x squared, -4i squared, guys. That's -4 times whose I squared? -1. So what's -4 times -1? +4. And it has now made an irreducible quadratic factor. That is a quadratic expression that will not factor and it will not reduce. All right? So technically, if you were going to write a polynomial that had these zeros, instead of writing these as your factors, because those are pretty weird looking, you most likely would write it as your linear factors that created your real zeros, and then you'd use your irreducible quadratic factor to produce the two imaginary zeros. That makes sense? Everybody okay? All right. So what I'd like to do, I want to say it's example 2, no. Let's go to example 3A because these ones are harder than the first two. So let's try these ones. The first two examples, guys, they're going to give you a polynomial function, and they're going to say find the complex zeros. Then they're going to want you to write it in factored form. So you're going to find your zeros, and then you're going to write them as linear factors. And if you had any imaginaries, then I would write them as that irreducible quadratic factor. You probably already had it before you set it equal to 0 and solve. I'll explain that when we get there. But these are just going to be find the zeros. Probably got to go through your rational zeros or go to the graphing calculator, use your synthetic and whatnot. So you're more likely you're not used to those problems. I've got to show you example 3, and I'd rather not get cut off by this one. Okay. All right, so example 3 says, use the given zero to find the remaining zeros of each function. So guys, they're going to give you a polynomial function, and they're going to tell you one of its zeros. We've seen this before. It's helpful. If they're willing to tell you a zero, then you know that zero creates a factor, and a factor will divide evenly in. And then you can divide it in, and you can start using your synthetic to break that polynomial down to a lesser degree. Normally, we're trying to get to that degree 2, or maybe a degree 3 or degree 4 that we could factor. The problem is they're giving you an imaginary zero. You cannot take that into a round of synthetic with an imaginary zero. So we're not going to be able to divide it in synthetically. So we're going to have to work around that. All right, so let's do this. This is a degree 4 polynomial that I cannot factor. And if you went to the graph, guys, it's degree 4. A degree 4 is even. That means both ends are up or both ends are down. It doesn't have to have any real number zeros. All 4 of these could be imaginaries. And then your rational zeros theorem did nothing for you. It didn't create any possible zeros on that list if they're all imaginary. So let's do this. We know it's degree 4. And that means there are 4 possible zeros. 4. We know one of them is 2i, which technically would create a factor of x minus 2i, right? Again, that's not normally a factor we would have come across, but it exists. What do we automatically know is another zero? Negative 2i, which we could say creates a factor of x plus 2i, right? Perfect. So guys, there's only 2 other zeros you have to find. Could they be real? Yeah. Could they be irrational, like 1 plus the square root of 5 and 1 minus the square root of 5? Yeah, and then again, the graphing calculator would not let us find that by hand because you can't find that on a graphing calculator. Or it'll estimate it and you want the exact answer. Could they both be imaginary? Yeah. So you really can't go to the graphing calculator on this one. So use what you know. I can't take these and synthetically divide them in because they're imaginary zeros. These are imaginary factors. But I know that they will multiply out to what? An irreducible quadratic. And we can take a quadratic and divide that in. The only problem is, the only way to divide a quadratic into that degree 4 polynomial is by long division. So you have to use your long division, and this is going to really, really bring back some algebra memories for you. And I know you guys said since COVID you feel rusty. So let's just try and take this one step at a time. So let's take these 2 factors and let's multiply them out to their irreducible quadratic. We just did it technically, if you remember in the warm-up. We got x squared plus 2ix minus 2ix, and then minus 4i squared, which then became x squared plus 4. Everybody okay? Okay, so we're going to take this. Guys, he's a factor. We got him from the zeros. He is a factor of that polynomial. So we know he will divide evenly in. So let's do it. We're going to take this irreducible quadratic and we're going to divide it into that polynomial. And we're going to be left with a smaller polynomial that hopefully we can solve for the rest of the zeros by hand. All right, so we're going to take x squared plus 4. Now it is missing 0 x's. You don't have to necessarily fill them in your divisor, who you're dividing by, but you definitely have to fill in any missing terms into who you're dividing into. You have to leave room for placeholders. So this has an x to the 4th, an x to the 3rd, an x squared, an x, and a constant. It's not missing any terms, so I don't have to fill any zeros in. But just like synthetic, if it didn't have any x's, then you would put this in here with a plus 0x in its spot. Because just because that polynomial doesn't have an x term, doesn't mean the other one that we're going to get doesn't have an x term. You have to leave room to placehold. All right, let's do it. X to the 4th minus 4x to the 3rd plus x squared minus 16x and minus 12. So again, I don't know how much you remember long division, even with numbers. And when you do it with polynomials, obviously everything becomes much more complicated. So I've written long division steps over here. First thing you do is divide. Then you multiply that in. Then you subtract, see what's left. You bring down the next piece, and then you repeat the process again. So to start this, the first thing you should do is ask yourself, take the first term of this polynomial and divide it into the first term of this polynomial. So how many times can x squared go into x to the 4th? Now sometimes that's like, what? I think of it like this. X squared times what gets you x to the 4th? X squared. So above your x squareds, because that's what we're going to do, we're going to keep ourselves organized, give yourself an x squared. That counts as the division step. How many times does x squared go into x to the 4th? X squared times. Now you have to multiply. So whatever you put up here, you have to distribute to this polynomial. So what's x squared times x squared? Okay, see how it matches? You want that. You always want the fronts to match, okay? All right, now what is x squared times positive 4? 4x squared. So underneath, right, we want to do like terms in the subtraction step, so keep everything nice and organized and aligned. So we've divided, we've multiplied, now we subtract to see what's left over. Now here's the tricky part with the subtraction. You have to pick up this subtraction sign every single time, and hopefully you'll see what that means when we're going. So what is x to the 4th? Subtract x to the 4th. 0, that's what you want. You want the first ones to cancel. That's from the division step, okay? What is negative 4x to the 3rd? Subtract nothing. Negative 4x to the 3rd, right? So bring it down. Okay, now this is the weird part. How many of you are thinking, oh my God, it's 5x squared, right? It looks like it, but you have to pick up the subtraction. What is 1x squared subtract 4x squared? Negative 3x squared. So that's where it can get a little confusing. You have to pick up the subtraction. All right, so now we've subtracted. Now, normally in like long division with numbers, you would just bring down the next number and repeat. I just bring whatever's left out. I don't leave anything. I don't want anything to not line up. So whatever's left after this, I just bring it all down. So now we bring down minus 16x minus 12. Let's do it again. So now we repeat. So now we're back up to the division step. So now you're trying to figure out how many times does x squared go into negative 4x to the 3rd. That's kind of hard. X squared times what gets you negative 4x to the 3rd? Negative 4x. So above your x's, give yourself a negative 4x. And it kind of keeps you like you're working your way down. All right. Now that's division. Now we multiply it in. What's negative 4x times x squared? Negative 4x, that's what we want. Guys, you always want that front to match because they're going to cancel in the subtraction step if they match. All right, what's negative 4x times positive 4? Yeah, negative 16x. Now, they matched. They did not have to. Only the fronts have to match. So please don't think like, these did not. That's just coincidence that those ones matched. All right, now we subtract because we're going to pick up that subtraction each time. and we're going to watch our signs. So what's negative 4x to the third? Subtract negative 4x to the third. What happens to minus minus? Turns to a plus, and they cancel, 0. We always want the first ones to cancel. What's negative 3x squared? Subtract nothing. Negative 3x squared. Okay? Negative 16x, subtract negative 16x. What happens to minus minus? Turns to a plus, and now they cancel. And then negative 12, subtract nothing, is negative 12. Now we have nothing left to bring down. However, we still have another spot there. There could be a just number factor. So let's do it one more time. All right, and again, the reason you have nothing left is because I bring everything down in one big step. All right, one more time. How many times can x squared go into negative 3x squared? Negative 3, right? Negative 3 times x squared would get you negative 3x squared. So above your just numbers, you need a negative 3. All right, now we go and multiply. What is negative 3 times x squared? That's what we were aiming for, negative 3x squared. Negative 3 times positive 4, negative 12. Now, when you get towards the end, guys, we created this factor from his zeros. We know he's a factor of that polynomial. So what does your remainder have to be since we know he's a factor? You've got to get a remainder of 0 or else you didn't long divide correctly. All right, or you didn't create the correct factor. All right, so now we subtract, and hopefully nothing will be left over because it doesn't look like I should have any more long division to go. Negative 3x squared subtract negative 3 is going to be 0. They cancel, turns to addition. Negative 12 subtract negative 12 turns to addition, and they cancel, remainder 0. So now you've been left with, he's a factor of your polynomial, and he will get you these 2 zeros. And now you have another factor of your polynomial, and he will get you your last 2 zeros. So all you have to do to find the remaining 2 zeros is solve that quadratic equation. Set that quadratic equation equal to 0 and solve. Maybe it factors, maybe we have to use the quadratic formula. All right, so let's set x squared minus 4x minus 3 equal to 0 and solve. Is it going to factor? Is anything going to multiply to negative 3 that adds up to negative 4? No. So we're going to have to use the quadratic formula. So I'd like everybody to plug this in to the quadratic formula and find your last 2 zeros. I'll do it up here. You do it down there. Now again, maybe they're imaginary, maybe they're irrational. Go ahead. Oh my God, Andreas, I'm so sorry. You didn't write any of that down. Okay, you do? I am so sorry. Just yell at me. All right, make sure you put your A's, B's, and C's into the right spot, into the quadratic formula. And then again, they usually ask you for exact reduced answers. So radicals have to be reduced, fractions need to be reduced. So I got the square root of 28. So now the square root of 28 can be simplified. The square root of 28 can be broken up into the square root of 4 times the square root of 7, and you get 2 root 7. So I'll put that in its place. And then everything in your numerator is divisible by 2, so we can divide everything by 2. Now remember, everything has to be divisible by 2. If this only divided by 2, don't lose the 2 that is his denominator. 4 divided by 2 is 2. Plus or minus 2 root 7 divided by 2 is root 7. So your last 2 zeros are 2 plus root 7 and 2 minus root 7. And again, the rational zeros theorems would not have helped us. All those P's and Q's only create rational possible zeros, and 2 plus root 7 and 2 minus root 7 aren't rational numbers. They're irrational numbers. So they would have shown up on the graph as probably some ugly decimals, but you would not have been able to use your rational zero theorems to create them. All right, how do we feel? That's a lot. Is everybody okay? Okay, let's go to B. Let's try it one more time. Yes?
How would you put the 2 root 7 into
I don't believe they're going to ask you to write these ones as factors, but if they do, you could always write it as the quadratic factor that created them, or, as weird as this is going to be, you could go back to the x minus 2 plus root 7, so all you'd have to do is add that over, and he's a 0, and then x minus 2 minus root 7, just like you did kind of with those imaginary complex ones. Just distribute your 0, and those are going to be your weird-looking factors. Okay? Perfect. All right. Now, guys, I did record this because I'm going to post it in case anybody wants to watch this back. You can fast forward to it in case you're getting stuck on the long division on your own. All right. So we have another degree 4 polynomial that it does not look like we can factor or solve by hand. They've given us a clue by saying 3 minus 2i is one of his zeros. So if it's a degree 4, we know there are 4 possible zeros. They said one of them is 3 minus 2i. So we know technically he could be a 0 of x minus 3 minus 2i. We know that. Who do you automatically know is another 0? 3 plus 2i. So now we know that he could be x minus 3 plus 2i, written as a factor. So there's 2 more zeros that you have to find. Do any of them have to be real? No. They could be 2 more imaginaries. They come in pairs, right? Only odd degree polynomials are guaranteed to have 1 real 0. If it's an even degree, all bets are off. All 4 of them could be imaginary zeros. Maybe they're 2 irrational ones again, and we still won't be able to find them on the graphing calculator. All right, so let's create an irreducible quadratic by multiplying it out and finding their product. They will multiply to an irreducible quadratic. All right, so I'm going to x minus 3 plus 2i, x minus 3 minus 2i. Now, I tried to show you guys yesterday this a plus b times a minus b. I don't know if I made any sense to anybody, if it helped anybody, but otherwise, you just got to FOIL your little heart out. So if you want to FOIL this like normal, let's try that. Everybody FOIL this out, and let's see what we get as this irreducible quadratic. Watch your signs. Bad stuff should cancel out. Again, I just take one term from the first parenthesis and I distribute it to everything in the second parenthesis. And you just create a laundry list of terms that you should be able to clean up, and bad stuff should cancel. Right? And there is my irreducible quadratic. It will not factor, there's no common factor, it doesn't reduce. That is our go-to polynomial now. So since we've created him from zeros, we know he's a factor. So that should divide evenly in. And again, if you divide a degree 2 into a degree 4, you should be left with a degree 2, which is our baby, where that's our quadratic. So let's give it a go. Let's take this and divide it in. Oh, I don't know. I'm gonna read myself through here. Now again, look at the polynomial you are dividing into. X to the fourth, x third, x squared, just x, constant, just number. It's not missing any terms. I don't have to fill any zeros in. And again, what should we get as a remainder? We've created this factor from his zeros. We should get a remainder of 0. All right. Are we ready? Do you want me to let you guys do it or should I walk you through? Because we've only done one. Just walk us through. Should we go together? Okay. Division first. How many times does x squared go into x to the fourth? X squared times what gets you x to the fourth? X squared. So above our x squared, let's put that. All right, that's the division. Now we multiply it in. So we distribute it here. X squared times x squared is x to the fourth. It matches. Guys, we want it to match. All right. X squared times negative 6 is negative 6x to the third. Beautiful. Now again, that matched by coincidence. They didn't have to match. Only the fronts do. All right. X squared times 13. 13x squared. Beautiful. Okay. Now we subtract, but you have to pick up that subtraction each time. All right, what is x to the fourth? Subtract x to the fourth. 0. Negative 6x to the third, subtract negative 6x, negative negative becomes positive, and they cancel. Great, didn't plan on it, but that's fine. 15x squared, take away 13 is actually what? 2x squared. All right, let's bring everything down. Let's do it again. Okay, so now, how many times can x squared go into 2x squared? 2, which is only a number, right? So now go above your just numbers and put a 2. So this could be our last step. We're at the back of the problem now. All right, now let's distribute it in. 2 times x squared is, beautiful, we wanted that to match. We need that to cancel when we subtract. 2 times negative 6x is negative 12x, beautiful. And then 2 times 13 is, oh, this is looking nice. All right, now we subtract. And let's see what we got. 2x squared, take away 2x squared. See you later. We want those to cancel. Negative 12, take away negative 12, turns to plus. They cancel. 26, take away 26. They cancel. Remainder 0. So there is your quadratic expression that you are now left with, your quadratic factor. So now we have this factor times x squared plus 2, and they will multiply out to that degree 4. So to find the last two zeros, we just have to solve this factor by setting it equal to 0 and solving. We know this got us those two zeros. So let's just set this equal to 0 and be done. All right. And you get plus or minus I root 2. So positive I root 2 is a 0, and negative I root 2 is your final 0. So again, here's a degree 4 polynomial. He had no real 0. So nothing would have helped you. The graphing calculator would have found nothing. The rational zeros theorems would have gotten you no leads. This had to be done using our division. So they had to give you that clue to get you started here. All right, do you guys feel okay? Yes? All right. Let's go back to example 1. If I can, maybe get one of those in, and we'll go from there. I'm gonna cheat on this one though. All right. So example 1 said, find the complex zeros of the polynomial function. So find all of them. Find the real, find the imaginaries, everything you got. Then they want you to write f in factored form. So I'm assuming they're going to want you to write f in his linear factors from your real zeros, and then your irreducible quadratic from your imaginary zeros. The book has updated, so I'm assuming that's still what the homework is asking for, okay? All right, let's do this. They didn't give you a clue. That means you should be able to either factor that by hand or use your P's over Q's to create a list of possibles, and somebody's going to work. So if you look at your graphing calculator, because that's what I would do, instead of making your P's over Q's, your factors of the constant over factors of the leading coefficient, right? Factors of 18 over factors of 3 to save you time. Don't do it. I'm going to cheat, I'll tell you. But I would go to the graphing calculator and I would look to see. All right? I'll tell you right now that if you create that list, -2 on the graphing calculator, I think it was -2. I won't lose. Yep, it looks like it's passing at -2. So let's try -2 just to save time. All right, so let's try -2 as a possible zero. And let's see if we're missing any terms. X to the 4th, x to the 3rd, x squared, x constant. We're good. Now, if you like long division, you could make this x plus 2, and you could long divide x plus 2 in. But this is a candidate for synthetic. Let's see what we get. It worked. So now that you've taken a linear factor, x plus 2, and divided it into a degree 4, you are now left with 1 degree less, a degree 3 polynomial. So again, degree 3s, they're hit and miss. Maybe it factors by grouping, maybe it doesn't, and you have to keep going in your synthetic list. So if you want, throw your coefficient, or your variables back in with your coefficients. This is 3x to the 3rd minus 1x squared plus 27x, and then minus 9. I don't know if you guys recognize, but that's a degree 3 that definitely factors by grouping. I can already see this common factor that they have in there that's going to be left. So you can stop the synthetic right now. Set this degree 3 equal to 0 and factor it by grouping. If you look at the graph again, there is another potential 0 in between, I believe, 0 and 1. That means it was probably a fraction, and there would have been fractions on your list if you want to create that list and see who the possible fraction was. Otherwise, I'm trying to get out of this as quick as I can. So I'm going to set this degree 3 equal to 0, and I'm going to see if it factors by grouping, because it looks like they got a lot in common. So if we factor it by grouping to get the last 3 zeros, because we already know -2 is one of them, let's see what we got. Group the first 2, group the second 2, and look for individual GCFs for each group. They have an x squared in common, and then that would leave them with a 3x minus 1. You go to your second group, you have to pull out the leading sign, and then what does a 27x and a 9 have in common? A 9. And then that's going to leave you with a 3x minus 1. So guys, it worked. You ended up with that common factor, so factor by grouping worked. So if you take the common factor out, you are left with 3x minus 1, and then who else is left if you take them out? X squared plus 9. And now you can set those 2 factors equal to 0 and find your remaining 3 zeros. He'll get you 1, he'll get you 2. Now, can I say something? These are factors of that polynomial. We just found out that -2 was clearly a 0, so he would have been a linear factor of x plus 2 potentially. I mean, again, maybe it was 2x plus 4, but it doesn't have to be unique at this point. So when they ask you to write that polynomial in factored form, guys, that's that polynomial in factored form. He's got 2 linear factors and an irreducible quadratic. So technically, that could be your answer to the last part of the question. And if you notice, it will multiply out x, 3x, and x squared to that 3x to the 4th, that leading coefficient that we need. All right, -2, we're going to get 1/3. And then we're going to get plus or minus 3i. So your 4 zeros to this problem are -2, 1/3, and plus or minus 3i. Those are our 4 zeros to this degree 4. Now they asked you to write it in factored form. So like I said, this, to me, is perfect. You don't have to set it equal to 0, though. Those are your linear factors and your irreducible quadratics, and they will multiply out to that leading coefficient, that leading term. Otherwise, if you start here, this is what you might get. X plus 2, x minus 1/3, not the best, and then you could say x minus 3i and x plus 3i. The only problem with writing it like this, these are their linear factors, but I am thinking the book is looking for your imaginaries to become their irreducible quadratic. So just go back to who you said equal to 0 and solve, and that's their irreducible quadratic. The problem with this is, if you multiplied your fronts out, do you get a 3x to the 4th as your leading term, your leading coefficient? No. So you'd have to throw a factor of who out in front? 3. Or, like I said, instead of writing him so weird, maybe write him as 3x minus 1, so you don't need that leading factor of 3. But either way, I don't think this is what the book is looking for. I think they are looking for this. Like I said, there's an update, so things have changed this year, and I was not able to go check. I think they're looking for your linear factors and your irreducible quadratic. Now, I don't see anything wrong with this because you still have everything worked out with linear factors and an irreducible quadratic, and you'll still get that leading power function 3x to the 4th. But I think your safest bet is this guy right here. Are you guys okay? All right, I don't think I'm going to be able to do the last one. Guys, I'm freaking out. You have homework from yesterday because the snow day. We have homework. I think I said due Wednesday, but I meant Thursday because I meant to give you 2 days, thinking yesterday was Monday. So yesterday's homework is due tomorrow. Today's homework would also be due tomorrow if we're quizzing on Friday. I'm afraid that I've really gotten a little too ambitious on you guys. I don't know if it's going to be possible for you to work on yesterday's homework if you haven't finished that, work on today's homework, look at a study plan that I've yet to post, that again would not be mandatory, and then quiz on Friday. Am I getting a little ahead of myself, be honest? No, yes, I'm seeing some shapes. So I was thinking maybe I would push the quiz to Monday. So that would give you, I could leave the homeworks open, I could open up a study plan, and it would give you the weekend to kind of wrap stuff up. Now again, I would leave the study plan as optional, but it would be there for anybody who wants to look over it. Does that sound like it would be more beneficial? Here's my problem though. The marking period is all screwed up because of the snow days. So originally it ended, I believe, today. And then they pushed it back to Friday, but then we had another snow day. I haven't heard if they've changed anything, but I really wanted it to be a quiz grade on second marking period. So I don't want anybody coming at me. She gave a quiz on Monday and she counted it for the second marking period. So I really want to end second marking period to it. So if I push it to Monday, I need you guys to understand it's going on second marking period. Is everybody okay with that? Yes? Okay. So I'll extend yesterday's homework maybe. No, yesterday's homework still isn't due till tomorrow. So that should be fine. But I definitely won't make this homework due. At this point, it won't need to be due until Sunday. And then I'll open up the study plan today. Does that sound like a plan? Okay. Yes. Okay. So technically, when we did this, our last two factors were 3x minus 1 and x squared plus 9. X squared plus 9 was the factor that got us the imaginaries. So instead of me writing this as x, like this and multiplying it back out, they are going to go back to that quadratic factor that you set equal to 0 and solved.
Like, how did you get that from?
Oh, okay. So when you factor by grouping has to leave you with this matching parenthesis. If it doesn't, it didn't work. So basically, when you factor by grouping, one of your factors is always going to be the one that matched, and your second factor will always be the two pieces you factored out. So I'll get 3x minus 1, the one that matched, and I'll get x squared plus 9 as my second factor. That's how grouping will always work. Okay?